Thank you, Chairman. I'm Whal LeeKR from Seoul National University. Today I will be talking about plaque segmentation rather than characterization. So I have a research fund from AI Medic and consultant of AI Medic and Eos Medical and Therabest, and also stockholder of Eos Medical Group. I have a patent about location adaptive thresholding for CT analysis, which I will be talking today. So I will introduce the vessel phantom study first, and then talk about TAG a little bit, why it is wrong, and new concept of coronary artery segmentation, and then at the last, calcium blooming. So this is my first phantom study for stenosis. Almost 20 years ago, I made this phantom with some stenosis. And then there is some stenosis we measured by X-ray, and I performed the CT scan and compared the stenosis degree by the CT and actual stenosis. Interestingly, the small vessel has overestimation of the stenosis. At the time, I used the full width half maximum method. That is when measuring the signal in general. As you can see in the CT, there is some hollow edge at the vessels. This hollow edge is a degradation of the pixel attenuation. So which part we have to measure? In that case, measure the center of the hollow is the correct way. That's the full width half maximum to get proper signal from the vessels. The problem is that when the vessel is small, actual attenuation of that vessel is decreased. So when we apply the same threshold for the full width half maximum, the small vessel actually disappeared. So small vessel has a low attenuation in same concentration of contrast media. This is the key. As we thought, the vessel filled with the same concentration of contrast media, we thought that the attenuation of the vessel will be the same, but actually not. Smaller vessel has a lower attenuation than large vessels. So stenosis is usually overestimated with the CT. That happens in our daily practice reading of coronary CT angio. CT is always overestimate the stenosis. Some cardiologists actually bring this concept, transluminal attenuation gradient, because they think, I'm sorry? Is this movie will working or not? No, okay. No, it's okay. So as a cardiologist, they always seeing some coronary artery filled with the contrast media by bit. So they assume that the stenosis may be a little bit obstacle for that flow. The proximal segment has a higher concentration of contrast media, and distal segment is low concentration of contrast media. They measure the attenuation, and the concentration of the contrast media affect the attenuation, and they think that will be related to the functional status. So this is reported, and many following report about transluminal attenuation gradient is reported. This is one of the first reports of TAG. Patient without coronary artery disease has a very flat attenuation changes. The patient with coronary artery disease has very steep attenuation change from the proximal to distal. This is another way sample for examination. But as told you, small vessel has a lower attenuation. Then what will happen? The small vessel distal has a lower than the large proximal. So I made another phantom. This is a disc phantom with a various hole from 5 millimeter to 0.1 millimeter to 0.1 millimeter interval. I immerse this phantom in a contrast media. That means all the hole filled with the same concentration of contrast media. And then measure the attenuation, peak attenuation of each vessels. What happens? As you can see, the 1 millimeter hole has with the same concentration of contrast media has only 100 Hounsfield unit, while 5 millimeter vessel has a 500 to 800 content. It's a 1/8 difference is huge. Interestingly, the vessel with a 3 millimeter has enough pixel in there, but still has a 20% lower than 5 millimeter vessels. So this means in the coronary artery, even with a very thick 3 millimeter coronary artery has a lower attenuation than 5 millimeter proximal segment. So let's review the previous reported. They argue that the TAG happens, but in the case of a patient without coronary artery disease, the vessel diameter is 2 to 4.5 millimeter, relatively big coronary artery. When they argue with the TAG positive, the vessel diameter is 3 to 1. It's a very small vessel, and the steep attenuation difference is expected. I'm sorry? Okay. The other case is the paper who argued that TAG is true. In here, the normal coronary artery without TAG has a 3 millimeter to 4.5 millimeter. It's a big coronary artery. Patient with a coronary artery disease, but also it has a small vessel, 3 millimeter to 1.7 millimeters. So, I'm sorry. Yeah, TAG wrong. And then the researcher on TAG said that, hey, well, it's real, it's a dynamic. It seems like that, but the truth is the diameter-dependent attenuation difference. I will show it. So I made the animal model. This is dog. I opened the dog's heart and strap the coronary artery, make some stenosis model and the occlusion model. And I do that scan that dog for cardiac CT, just multi-phase for 25 seconds scanning, hold the heart repeatedly, and then measure the attenuation of each coronary artery. As you can see, with the time, the distal coronary artery never reaches the attenuation to the proximal. That means the distal coronary artery always has a lower attenuation in the proximal, even though there is a coronary artery stenosis or not. In case of occlusion, the distal segment is sometimes higher than the proximal in some moment. So when we measure the TAG, normal LAD has a rapidly decreased diameter, has some degree of TAG, but our circumflex artery is big in dogs, so they do not show any TAG without stenosis or with stenosis. So regardless of the stenosis, it depends on the vessel diameter. In case of occlusion, you can see some reverse TAG, so depends on the timing. I will also do some research on the human. The proximal segment has some stenosis. In there, the attenuation is dropped because the small vessel has a lower attenuation. In distal segment has already TAG, but as you can see, the TAG is also compared with the TDG, so trans diameter gradient. So diameter is also decreased, attenuation is decreased. That not comes from the stenosis. So in human study, the TAG has a p-value is insignificant, 0.884, but diameter itself is relatively to stenosis, that's 0.02. So we can conclude that TAG is a secondary result owing to difference in the coronary artery diameter by phantom, animal, and human researches. So size-dependent attenuation difference is an important key concept. This is not just for TAG, but also can used for coronary artery segmentation. Coronary artery segmentation is more and more important because we are now using CT-FFR and the plaque volume measure. CT-FFR is actually comes from the coronary artery segmentation, and after coronary artery segmentation, computational flow dynamics is applied. And when we measure the plaque volume, it's also a matter of coronary artery segmentation. Let's remember this scan adaptive threshold method. We applied a single cutoff value from the half maximum full width half maximum threshold. The small vessel will be overestimated. Rather than this is a location adaptive threshold method. So each vessel has a different central attenuation. We have to apply different threshold for measuring that small vessel. That's a location adaptive threshold method. So for the coronary artery segmentation, the threshold should be changed slice by slice along the coronary artery. This is some pixel demonstration of the scan adaptive threshold and the location adaptive threshold. When you apply the scan adaptive threshold, we have to apply the same 800 attenuation for the vessel segmentation. But when we apply the location adaptive threshold, we can apply different threshold for each vessel location. So the orange color area is a vessel, is a huge difference in the segment of stenosis. So first we have to do is a center line determination, is the path determined by center of gravity. And then we have the function of a house building unit made and export to the Excel file. And we determine the threshold of each location and then measure the vessel area from this. So validation of a new concept using clinical data. So we need a gold standard. IVUS is gold standard. So we select a patient who underwent IVUS and plaque volume. So we can measure the plaque volume by location adaptive threshold and also scan adaptive threshold method. When we compare with the IVUS, the location adaptive threshold shows less bias and a smaller divergence from the gold standard. And also lumen volume is very similar to IVUS when we apply the location adaptive threshold. So plaque volume is also quite similar in case of location adaptive threshold. So the location adaptive threshold is almost identical with IVUS, where scan adaptive threshold overestimate stenosis, that means also overestimate the plaque volume itself. Actually, this phenomenon depends on the vessel size. Vessel size is more than 7 millimeter. This effect is already decreased. The location adaptive threshold and the scan adaptive threshold shows almost same result. But when the vessel size is less than 7 millimeter, the location adaptive threshold is better than scan adaptive threshold. So I can make this conclusion. Location adaptive threshold concept is proved. And let's apply to the real tool. So we made a software with some company, and then automatic segmentation for the lumen and vessel was done, this software. Also, the single via from Siemens and IntelliSpace Philips segmentation of coronary artery plaque was applied and compared with the IVUS. So the interval for this research was IVUS is 0.01 millimeter, single via is 0.25 to 0.5 millimeter. Philips one is 0.3 to 0.4. Auto segmentation is 0.2 and 0.4 segmentation millimeter slice thickness. So all the coronary artery has it's a ribbon reconstruction has its own coronary artery axial images. We measure the plaque volume in each slices. The lumen area, when we make the blend alpha plot, the software 1, that means the location adaptive threshold method shows the bias closest to 0 and the lowest standard deviation for lumen, and also for the plaque. When you compare with the Pearson correlation coefficient and the ICC, the location adaptive threshold shows the best result for both of them. So this is some of my research about the coronary artery segmentation, new concept that is location adaptive threshold. So you can apply this method when you read coronary artery CT angioscan, because you have to know small vessel has a low attenuation with the same concentration of contrast media in there. So I moved to my intention to calcifications. Calcification is always problematic, like this. So we saw calcification on the right coronary artery proximal segment, but in coronary artery scan, the coronary angiography, there is no stenosis at the segment. That means the calcification always looks big than usual, and then we should be careful about the interpretation of the coronary artery segment with calcification. Calcium uncomputed tomography always is a problem. I copied these images in some guideline published by 2016. There's a solution for calcium blooming is increased tube potential. And in some article also recommend high KBP for coronary artery stent. So I try to measure that by phantom. If we increase the tube voltage, to 140 that really decrease the calcium blooming. So I made this phantom, various size of phantom, and then do CT scan for that, and then actually measure that. Interestingly, full width half maximum is already a bit underestimate calcium, surprisingly. So I applied the full width third maximum to make correct value from the calcification. So all the measure from the CT is full width third maximum from these researches. So let's compare with the 80 kbp to 140 kbp. So vessel, the calcium diameter measured on each image, the pixel, is almost same. 140 kb actually a little bit higher diameter than low kbp. So calcium blooming can be solved by high kbp? Is not. I try to another approaches. If the diameter of the phantom is always same with a different attenuation, what is the blooming of the calcium? So I made another concept. So we know exact diameter of the calcium phantom, but the other surrounding the pieces are a bit higher attenuation than the background. That's blooming. So I measured the blooming area. If the high kbp has a higher blooming area, I tried that, but the blooming area is almost same in 150 millimeter FOV. I doubt large FOV like extremity has more calcium blooming, so I tried it in 300 FOV. So large FOV calcium pixel is small. It's also, there is no difference between the kbp. As you can see, large FOV shows a little bit higher blooming area because the pixel dimension is a little bit big, but there is no difference from the kbp. So I think the different kbp does not give us any benefit to reduce the calcium blooming. And also that's true in the stent. I did not introduce the stent, but I applied also the research about stent is not changed. So calcium diameter comparison using kbp 100 compared with the other diameter of the vessels. Is a large vessel has a higher blooming area and small vessel has a smaller blooming area? No, the blooming area not depends on the vessel size. This is a shape. So if the curvilinear shape has a higher blooming area, no, it's also same. So in the phantom, calcium always shows the same degree of a phantom. That means my time's up? Okay, 2 minutes. So the stent-like feature is the degree of calcification. If the vessel lumen is almost very small and then it's just a curvilinear wall calcification, it also blooming is the same. So my conclusion of this research is actual size of calcification can be measured on the CT image without proper window width setting. The size of calcium and blooming artifact is the same on low and high kbp. Why we have that, see the blooming? That's because inappropriate window setting made a reason for the misconception. Means a low kbp has a higher attenuation. We have to apply the wide the window. With the high kbp, the attenuation goes down. When you apply this wide window, it's a little bit proper window setting the high kbp. So if we do not change the window width, high kbp give us the low attenuation, looks like blooming looks smaller, but actually when we apply the proper window width or actually measure the pixel itself, the blooming is not changed. So the blooming area from calcification is significantly decreased with small FOV, but not from the high kbp. So try to use a smaller FOV for cardiac scan, but using high kbp is not solution. How about the virtual monochromatic imaging? I tried that with the dual energy CT. So try to the virtual monochromatic imaging and try that. The blooming artifact from calcification is decreased when using the dual energy CT, but look at this image. There is some already black hollow surrounding the calcification. that means a somewhat overshooting correction of that. So it is already decreased the calcium area, but give us other artifact around the calcification. So I don't think this is also, I think this is also not a solution for the calcification. So in summary, smaller buster has a low attenuation in same concentration of contrast media, keep in mind. And location adaptive stress holding concept for coronary artery segmentation is important for correct measure the vessel lumen and plaque. And calcium blooming is quite mystery. I don't know what happened this, so I'm still digging up the calcification blooming with the phantom and the human data. So thank you very much.